All right, this is Mr. McMurray again, although you didn't hear me the first time because they blocked my video because I used the music video at the first, just a smidgen of it, and it got me into copyright issues, I guess. So we'll just play our own music. All right, I'm pretty sure that's not copyrighted. Anyhow, we'll see. If you don't see this, then you'll know that it was copyrighted and they blocked it. All right, anyhow, here we go. So we're going to talk about work and power, but first we have to talk about energy because it takes energy to do work or to have power. All right, and what is energy? Energy is kind of a hard word to define because fire, heat is energy, but so is electricity, and so is things that are moving, like my hand, they're moving all over the place. They have kinetic energy. So what do all those things have in common? Well, it's kind of hard to come up with a definition. We know what energy is, but we don't know how to say it, all right? But best answer we're going to say is the ability to cause change, all right? Because electricity, heat can all cause changes. Motion, something runs into something else after motion, causes change in location, all this stuff. Now, this is a definition that primary is used in chemistry because it's all about chemical changes or chemical reactions. All right? So the ability to cause change. It also causes change in physics, but usually we talk about in terms of physics is the ability to do work. In other words, if you have energy, it enables you to make changes by doing work on something, all right, getting something accomplished. All right, so we will talk about work and exactly what that is here in a momento, but you should know that this is measured in units called joules, Joules, no Jewel. That's a different kind of joule. This was named after, I believe it was a French scientist who discovered the concept or explained a lot of the concepts about heat. All right. So energy is used to do work. So let's talk about work. What is work? Well, work is the transfer of energy that occurs when a force makes an object move. Ooh, wow, that helps. No, it does kind of help if we break it down. Basically, you're using force and it transfers energy from you to something else, okay? And it makes something move, all right? So in order for something to be work, there's a couple of requirements here, pretty basic. One, the object has to move, okay? So for example, I can push against this wall as hard as I want. Now, am I exerting energy? Yes. Am I going to get tired? Yes. But is the wall going to move? No. And if it doesn't move, then no work is done. Someone says, but I'm working hard. I get tired. No. It's not considered work unless something moves, okay? For example, there used to be a lot of exercise that people could do that made for people who were sitting at their office, and they could push against their hands like this and push against their head and get their neck. And it was good because it gave you exercise while still sitting still. But technically, according to physics, you weren't doing any work. You weren't doing any work at work either because you're doing these exercises. But if you're sitting at a desk all day, it was a good way to get exercise done. But technically, according to physics, you were not doing any work, okay, even though you were exercising those muscles and getting them tired because nothing is actually moving. And it's called isometric, same place, okay, same measurement. You're not moving anything. You're not going anywhere. All right. The other thing is the object must move in the direction the force is applied in. So, for example, if I have my speaker here, which I have turned off so I don't get into copyright trouble, all right, but if I have this speaker, all right, and it's in my hand, all right, if I get up and I walk with this, the object is moving. But that is not considered to be work. So, what? Why not? Well, because I am putting a force on it with my hands, but I'm pushing it up. But if I'm just sitting here in my hands, is it going up? No. So it's not going in the direction of the force. So my hands are not doing any work on it. Now, when I walk with it, you could argue that my feet are doing work on my whole body and anything I'm holding because it's moving my whole body and I'm going in the direction of the force that's pushing me forward. Okay, so my feet are doing work on it, but my hands are not because it's not moving the object in the direction of the force. I'm pushing up on it, but it's not going up. Now, if it went up like that, then I would be doing work. Okay? All right. So the formula for work then is work is equal to force. You have to have a force on it, applied it in a certain direction, which means it is a vector quantity, and it has to go a certain distance. Okay? And in order to go a certain distance, then that's what we talked about. It has to be in the direction of the force being applied to it. All right? Now, because of that, since we measure force in newtons and distance in meters, we would measure work in Newton meters, Newton times meters. That's what the little symbol there stands for. Let me find one more thing. Okay, Newton dot meters, so Newton time meters, or people say, well, it's kind of messy to use that, so let's come up with its own name and call it joules. Once again, guess what? After the French scientist, and symbol is a capital J. All right, it's the same as energy, which makes sense because this way, if we know how much work we need to do, we have a certain object that we need to move a certain distance, then we can do that, and we can figure out how much energy we need to produce in order to make that happen. Okay, if we know that we have so many joules of work to be done, then we have to make sure that our machine has enough energy supplied to do that work. All right. All right. So there we go. Now, power. Power is a little bit different. Power, ha ha ha, I'm in charge. Oh, no, that's different. That's a different kind of power. Okay? Teachers sometimes get that power and abuse it because they're in charge of the classroom. So they can make you do whatever you want to. Now, that's a different kind. If you watch pickup commercials, you talk about, oh, more power, Ram or Ram Dodge or Chevrolet or Ford, F-150, whatever. They all have more power. What does that mean? Well, on a commercial, not very much, probably, okay? They don't really know what that means. But officially, according to physics, power is the amount of work done in a certain amount of time. So it's how much work you do and how fast can you do it, okay? So the amount of work can affect the power, and how long it takes you to finish it can do it. So if you want to see if two pickups were equally powerful, you could load them up with the same amount, so it takes the same amount of force to pull or move that object, and then you would measure how long it took them to go a certain distance. And whichever one could do it faster, according to physics, would have the more power. And it could officially be because of the time there. Okay? So it all has to do with how long it takes. So power is equal to work divided by time. Or, since work is force times distance, it could be force times distance divided by time. Either way, that would get you the answer. So you could increase the power by doing more work. If this number gets bigger, you have more power. And if you do it quicker, you also have more power. So the smaller the time, the bigger the work. So work and power are directly proportional. Time and power are inversely proportional. The less time it takes, the more power you have. All right? Now, the units for power then are Newton meters divided by seconds, since time is measured in seconds. Or if we do that in joules, it'd be joules per second. But once again, to make it more compact, they said let's make up our own unit for that. And so joules per second or Newton meters per second are also known as watts. Now, when do you normally think of using watts? What is a watt? Well, a watt is a watt. There you go. And that's watts watt. Whew, that was bad. Sorry. Okay. Anyhow, watts have to do with power. We usually think of watts, we talk about a 60-watt light bulb or whatever, okay? And talking about the power it takes to light up a light bulb, all right? So it can be used for any kind of power, using for objects that move. It was named after a man who invented a steam engine, all right, James Watt in England, and that pretty much started the Industrial Revolution and much more powerful factories and so forth, things that could be done because of that. And so it was named in his honor of watts, because they measured the power that those machines had. How quickly could they do certain jobs? And because they could do it much quicker than horses and other ways that they had up until then, it really revolutionized the world at that time. All right, but anyhow, his name is Watts. And so it usually is used by things that actually do things and move a distance and whatever. But in electricity, when I turn on the light, what moves? Well, the switch moves, but my turning the switch on doesn't make the electricity. It just allows the electricity to flow through it, but it doesn't create the electricity. So it's not coming from my work or my moving the switch a distance. So what gives? Well, there's a special definition then. If energy is transferred, like electricity, without you doing any work, putting any work into it, then we have a different formula. And we just say power is equal to the energy divided by time. All right? And so that is the definition for power. And if you talk about your power bill, your electricity bill, it will be measured in kilowatt hours, but it's measured in how many kilowatts you use, okay, and for how long do you use them. All right. And so a more powerful house would have use more energy and do it in less time. But since everybody gets the same amount of electricity coming out of their sockets, 120 volts, or if it's a washer dryer or something like that, you might have a 220-volt outlet. That really doesn't apply so much. The energy is pretty much fixed, how much is coming out. But kilowatts are used. We use kilowatts because we use so much electricity. Very rarely are you going to measure things in actual watts. All right, whoa, hang on. Let me do that back a little bit. All right, first of all, a machine. We use machines to do work, and because we can get, or to use power, okay, to do things quickly. So a machine is just a name for a device that makes work easier for us. Okay, and there are 6 main types, which we may talk about later after we come back after the break. We'll see. But a device makes work easier on us. Now, notice it does not change the amount of work it takes to do something. If something takes a certain amount of work, it will still take that much work even with the machine. It's just it makes it easier for us to do the work. Okay, and so let's look at how that does that. Okay, a machine cannot change the amount of work required to move the object a certain distance, but it can help out. Okay, now a couple ways it can do that. One is a broom. Okay, let's look at a broom. All right, if I'm sweeping with a broom, I'm putting force on the handle right here, and it's moving the broom a certain distance down there. Okay, now it actually takes more force to push the broom here than it would if I just touched the broom down here. It's actually easier down here. It's harder up here. It's kind of like opening the door with the doorknob that's next to the hinge. It's really hard. It can be done, but it's hard. Okay, someone says, well, why would I want a machine that makes it harder to do it? It takes more force. Wouldn't that make it harder on me? Well, it would, except for, here's the deal. When I sweep, I move my hand about 3 or 4 inches. But the broom moves 3 or 4 feet. All right, so for every inch I move up here, it moves a foot. All right, so it multiplies my distance. Even though I have to use more force up here and move a short distance, it'll make the broom exert less force, but over a bigger distance. And if you're trying to sweep, I want to get done with sweeping so I don't have to use the broom anymore. And the more distance it covers, the quicker I get done. So in that case, we are actually going to have to put in more force, but we only have to move it a short distance, and it multiplies the distance the machine moves, okay, down at the bottom. So we say it multiplies the distance. All right. Now that's probably the less common one, because unless it just takes a little bit of force, like the broom takes a relatively small amount of force, we don't mind having to input more force. But most of the time we want machines that the part we have to do is we put the force into it. So we want it to decrease the amount of force we put in, but increase the distance. All right. And so we're going to use this fancy machine right here, which is a hammer. Okay, if we take this hammer and I pull on the hammer, okay, there's 2 works being done. I'm putting work into the hammer. I put a certain amount of force on the handle, and I move it a certain distance. Okay, all right. There's also force that the hammer is putting on a nail. Assume this is not my hand and it has a nail in it. All right, it's a board with a nail. All right, when I move this, the hammer head moves a certain distance, maybe about an inch or so, and it exerts a force on the nail. All right, and these 2 forces are roughly the same amount. So over here, if I have a big distance, let's just say I go 8 inches, okay, and a relatively small amount of force, well, if I only move the nail up 1 inch, in order for it to be the same amount of work, that means it puts 8 times as much force on the nail. So it puts 8 times as much force as I put on here, and so it puts a lot more force, and that makes it easy for me because I don't mind doing a small force for a bigger distance because it's not much force. It's not that hard, and so I can do that, and it will pull the nail up. All right, so in that case, we're saying it multiplies force. So you're using less force, but you have to move it a longer distance, and it will make the machine put more force over a short distance, and therefore it makes it easier on me because I have to put the force in. So we say that multiplies our force. So I put a little bit in, and it puts out a whole lot more force on the object. All right, kind of like a ramp or stairs. If you go upstairs, it's a lot shorter, but it takes more force or energy to lift yourself up to the top of the stairs. If you go up a ramp, they're really long, but it's a lot easier to walk up the ramp because it's not very steep, and so it's a lot easier to go up there. You use less force, but over a longer distance for ramp versus stairs. Okay? All right, and the last one is like a lever, and that is where it changes the direction, pulley, excuse me, not lever, changes the direction of the force, and we will talk about that in the next notes that I am going to record. But that's it for now. Have a great day.